All right, so welcome everyone to day 2 of our data camp. We're going to kick things off here with our first session on understanding the CCSQ data and analytics environment. But before we get started, I just want to remind everyone, if you have any questions during the presentations, feel free to put them in the chat. They'll be answered during the Q&A portion at the end of each session. Also in the chat, I did post a link to our Confluence page. There you can find the agenda for today, as well as the session summaries. And of course, if you have any issues or questions during the event, feel free to just message me in the Zoom chat and direct message, and I'll be able to help you out. So at this point, I'm going to hand it over to our speaker for this session, Philip Pham, to kick things off for us. Now to you, Philip.
Hi, everyone. Thank you for joining the session today. In the next session, we'll be talking about the CCSQ environment and what the CDR and CAP systems consist of. And at this point, Rachel, are we going to be playing the recording?
Yes.
Okay, excellent. Hi, everyone. Thank you for joining today's session. In the next hour, we will be going over the CCSQ environment to provide an overview of its current subsystems, how we are deployed in the cloud, and how its key services are used to power your analytics workflow and needs. We will also be covering the architecture of key technologies including AWS, Apache Hadoop and Hive, Apache Spark, and SAS Viya before summarizing how all of these services work together. So in the first section is CAP and CDR. The CCSQ environment is comprised of two major components, CAP, which stands for CCSQ Analytics Platform, and CDR, which stands for Centralized Data Repository. Both of these subsystems are deployed within the CCSQ Amazon Web Services Cloud. And you can think of CAP as the set of applications that you will be accessing in order to write your code, configure your jobs, and develop your models. CDR, on the other hand, is the data warehouse that stores all of the critical data sets across different CMS programs for your analytics. And that is powered by a distributed processing engine in order to run all of your SQL queries to be able to access the hundreds of millions of records across hundreds of terabytes of data. Both of these systems are independent, but work hand in hand to support your analytical workflows. And it is our priority to ensure stability, resilience, and scalability within each of these subsystems in order to provide you access to rich capabilities and a good user experience in order for you to produce your deliverables and to meet your timelines. Next, I'll be going over the architecture within AWS and highlight a few of its key services within our system. But before I do, I want to provide you a little bit of history on what AWS or Amazon Web Services is. So that platform is one of the leading cloud computing platforms that includes infrastructure as a service, platform as a service, and software as a service offerings. And AWS was launched back in 2006 from the internal infrastructure that Amazon.com was built upon in order to handle its online retail operations. And when it went to market, it was one of the first companies to introduce a pay-as-you-go cloud computing model that scales to provide users with compute, storage, and throughput as needed. The use of AWS has been invaluable to us in the CCSQ community as it provides us immediate access to on-demand resources for compute and storage that could take otherwise months to procure, set up, and configure if our systems were deployed in an on-premise data center. Moreover, By being deployed within the AWS cloud, we have the opportunity to tap into the latest and greatest technologies that AWS has to offer to be able to speed up all of your analytics processing and provide you with more advanced tools and software to improve your productivity. So this next slide highlights a couple of the key services that we use within CAP and CDR today. The first of which is a storage service called Amazon Simple Storage Service, otherwise also known as S3. So S3 is used to store data objects within buckets that can be directly accessed through other applications. And it can store any type of file formats including text, CSV, JSON, Parquet, and any other large data set file types as well. The advantage of using S3 buckets is that it provides us unlimited capacity and also supports other features such as secondary versioning of objects for recoverability and other server-side encryption capabilities as well. Another storage service that we are actively piloting right now to explore is Amazon FSx for Lustre. This particular product is a high-performance file system that can be backed by S3 buckets. And with this particular product, it reduces the latency of access to datasets that are stored within S3 so that it can allow your applications to run faster and more quickly. A third key service that we leverage within our environment today is a computing resource called the Amazon Elastic Compute Cloud, otherwise also known as EC2. EC2 is a scalable infrastructure as a service platform used to host application and services. And EC2 servers can be provisioned in a wide variety of sizes depending on what the computing needs are for your use cases so that users can access applications such as Hadoop, Hive, Spark, and SAS Viya Services today. This next slide has a diagram that illustrates at a high level how some of those key services are accessed in the cloud. So starting with the top, as a CCSQ user, from your local computer, you can log into a CAP application that is configured within one or more EC2 servers. And from that session, you can write your code to be able to access CDR datasets that are stored within S3 buckets. For faster access, however, to these datasets in S3, you can also read files into your application using the Lustre file system towards the bottom that you see there in order to increase your job runtimes to complete them more quickly. One takeaway from this illustration is to remember that when you are working interactively in a cloud application from your desktop, that development depends on a stable, consistent internet connection in order for you to have a smooth user experience. Because if your internet connection breaks at any point, your development may become disrupted as well. Moving on to Hadoop and Hive services. Apache Hadoop is a framework that is used to efficiently store and process large data sets ranging in sizes from gigabytes to petabytes of data. And the entire framework is based on the premise that instead of using one single large machine in order to store and process data, the Hadoop framework allows clustering of multiple servers to analyze massive data sets in parallel more quickly. The Hadoop framework consists of many different services, but the ones that are most relevant for us that you should be aware of are ones related to processing and storage. So within processing, it's powered by a MapReduce framework, and on the storage side, it's powered by a distributed file system that we use today that is backed by AWS S3 buckets. So a little bit more information on what the MapReduce processing is that it is a processing philosophy within this framework that facilitates concurrent processing of large data sets that include map and reduce stages. So the map stage is the stage within the workflow where large input data sets are essentially split into smaller blocks and assigned to mapper tasks for processing, in which in those tasks they are essentially tagged with keys. Those keys are used in reduce stages to be shuffled and sorted by so that the record values can be aggregated for that key. In the diagram in the illustration below, you can see essentially how the workflow is facilitated by starting on the left side. If you have an input data set in that green box with records such as XBB, CBA, and XAC, within the specific map stage, it starts off with that split operation where the records are split first separately. And then from there, those records are streamed into map tests where the records are essentially tagged, splitting out things like XBB into the X key, B key, and B key. And then same thing for CBA. Those are split out continually again across CB and A records, tagged with the initial value of 1, and the same thing for XAC, split up and tagged with the value of 1. In this illustration, it also has intermediate stages that are optional, that include combine and partition. But the most important takeaway is that from the keys that are outputted from the map stages, those are essentially shuffled together, sorted by key, as you can see that's happening, where records following the same key are combined together. And then once they are combined in the same specific task, they can be aggregated so that at the very end, within the reduce stage, the total number of records where all of the records have been aggregated based off of keys A, B, C, and X can be aggregated together so that they can be summed up in this particular illustration. In this example, it is showcasing the use of MapReduce to be able to do simple operations such as counting records, but I'll be showing later on in this demo and presentation other instances where the MapReduce processing can be used to support other operations related to SQL. Moving on to the storage philosophy behind Hadoop is that in one scenario, in one configuration, you can leverage the Hadoop distributed file system, otherwise known as HDFS, to store all of your data sets that allow for your data objects coming from your files to be replicated across machines. However, in this configuration, it is limited to the disk space that's available on the EC2 servers and machines that are a part of your Hadoop cluster. So an alternative configuration is that Hadoop supports an implementation of HDFS to support reading and writing regular files directly from Amazon S3 buckets. In this configuration, it allows access to the unlimited storage capabilities that we have by using Amazon S3, while also taking advantage of other features, including the Amazon S3 server-side data encryption. So I can see here, there's advantages to leveraging the Hadoop cluster configuration with storage powered by Amazon S3 in the bottom right, where we are able to separate out our storage layer from the processing layer that are powered by the EC2 instances. And this is further illustrated in the next slide, where with this particular architecture and the separation of those particular layers, it allows us to manage those resources independently so that we can scale each of them appropriately with our needs. And to put this into layman's terms, when there are high periods of high activity to support your processing needs. This allows us to essentially expand out our processing layer as needed. And when those jobs have completed, it gives us the flexibility to elastically scale them back down in the future. And by using S3 buckets, of course, as the storage layer, no longer having to be tied back with the disk storage that's on the EC2 machines, we have access to the unlimited capacity, as I mentioned before. Next, we can move on to the critical Apache Hive service that's a part of CDR today. A little bit of background within Apache Hive is that it's a data warehouse project that's built on top of Apache Hadoop that provides users a SQL-like interface in the form of the Hive QL interface to query data that's stored within databases and tables that are managed in a Metastore within the Hadoop framework. And with Hive and this SQL interface, users can submit SQL to be executed. And what the Hive service essentially does is analyzes that input SQL to build a query plan in the form of a directed acyclic graph, or DAG. And a DAG consists of vertices and edges where each edge is directed from one vertex to another, and that every edge is directed from earlier to later in the sequence to execute your workflow using the MapReduce philosophy. In the bottom there, I'm showing what a sample SQL query can look like, where someone may submit a select statement to retrieve all the records from table number 1 joined with table number 2 on table 1's B_ID column against table 2's ID column, filtering all the results where columns and records in the table 1 has a value of 1, and within table 2 has a value of 2, and you're selecting out all the columns in table 1. So for this sample SQL, it can be interpreted by the Hive service in the corresponding DAG that you see on the right side, where as it takes the specific inputs, it identifies that it needs to be able to retrieve records from 2 different tables. So at that point, it can split up the workflow to 2 separate map operations, in which each map operation is pulling records from 2 tables. And then when it retrieves those records, you can take it on sort of to that next stage where those are split up into specific keys. The keys being tagged by the columns that are needed in order to be able to do your join. So looking back at the SQL, that's going to be the B_ID column within table 1, and then the ID column within table 2. And then once those have been tagged appropriately, there's the reduce stage where all of the records are essentially kind of shuffled together, organized and ordered by their key, so that eventually all of the records that you get from both tables are merged and sorted together to be completely reduced, where at the very end of the reduce operation, the records that get returned to the specific query are ones that match the condition of your join logic. And then as a result, you are only pulling all of the column, the fields and values coming from table A, as you can see in the SQL. So all of this complexity and sort of that analysis is all part of the Hive services. And as it is executing this particular DAG, it is able to execute all of the operations in parallel to one another across all of the EC2 instances in your Hive cluster. Moving on to the Metastore. The Hive Metastore is the central repository for CDR that contains all of the metadata information about databases and tables in a Hadoop cluster, including the schemas for the databases and tables, its partitions, the object formats, and even the locations where those objects are being stored within S3. Within Hive, the Metastore is used to determine where to fetch all of those data sets, taking all that metadata information. And depending on what formats those objects are in, are used to determine how they can be deserialized and serialized during the MapReduce processing. So in the illustration I see in the below, you can kind of view it as CCSQ users from the CAP applications will submit SQL queries to this Hive server. The Hive server translates that Hive QL statement, and when it determines what tables need to be queried, it looks up those tables to make sure they exist in the Hive Metastore, and then pulls all the metadata information that's relevant in order for the EC2 instances to be able to execute against. And this, in the next slide, it shows an end-to-end use case here where it showcases that Hive architecture that I kind of described, where starting with the CAP application, and in this case, SAS Viya, which I'll be going over later. Within SAS Viya, users can execute macros, including that Hive _exec SQL, where they pass in their Hive QL statement, and through the JDBC connection that SAS Viya makes to the Hive service, it submits that query to the Hive server, where it's connecting to the Metastore to look up all the appropriate information and metadata surrounding the tables and databases that need to be accessed. And then it is coming up with the query plan and a DAG to be executed, in which it pushes that information down to the EC2 servers that are in the Hive cluster. And within that processing and resource management layer, those EC2 servers and all of those mapper tasks and all of those reduce tasks that I showed earlier in the DAG, all of those tasks are pulling information and data from the distributed storage in Amazon S3 buckets, where the location information from the Metastore has been collected, and the corresponding records from all of the data files are pulled back on the EC2 machines, getting tagged with appropriate keys, shuffled, passed on to the reduce operations to finally get to the resulting data sets to return back to the Hive service and essentially back to the SAS Viya system in that specific query. Another key technology that I want to highlight today is Apache Spark. Apache Spark is the big data processing framework that has evolved from MapReduce, which includes an in-memory data engine that speeds up processing. Within Apache Spark, its DAG supports multiple stages, and compared to Hive, those particular tasks and those stage executions can be more evenly distributed than just the simple MapReduce framework itself. More importantly, however, is that with Spark, it has robust APIs that allow for the support of other languages in order to take advantage of its distributed processing framework. And this includes being able to write code within Python, in the form of PySpark, being able to write R code, which can be executed with Spark R, as well as Java and Scala. And the usual way that folks are developing Spark code today is to be able to take advantage of notebook technologies, including Jupyter notebooks, Databricks notebooks, as well as SageMaker notebooks. And in each of these particular tools, users have the capability to create a notebook for their particular project, writing code either in Python, R, Java, or Scala, and then when those notebooks have been created, can be run using the Spark framework to have certain operations such as count, execution and operations, aggregations, and analyses to be distributed across multiple machines. And so this technology is extremely important because it breaks down the previous paradigm that jobs and code within Python, R, Java, and Scala only can be run within a single machine. And with the introduction of Spark, it allows the processing to be distributed across multiple machines to allow you to handle large workloads of data sets and expensive operations that may require more CPU and more memory than can otherwise be provided by a single server. The next slide shows what that architecture looks like. So kind of looking at the bottom there, you can see that there are key components to the Spark architecture. Similar to the Hadoop and the Hive architecture, there can be multiple machines in a Spark cluster. And all of the processing starts in this cluster within the master node before getting distributed within the worker nodes to run your operations in parallel. In this architecture, Spark jobs start with and run with a driver program that's located running within the master node. And within this driver program, it creates a Spark context instance that communicates with the cluster manager to be able to execute the job. So when your job is getting executed and the logic is being run line to line, there's essentially a distribution of all of those operations within your code that distribute certain operations, expensive ones, to all of those tasks that are running within the worker nodes. And within each task, within the worker node, it has access to its own cache as well, so that it would, in order to reduce the amount of data that has to be transferred across the network. So up to this point, I've spoken about the importance of Hive. I've spoken about the importance of Spark as it relates to the Hadoop architecture. One takeaway from this is that it's important to not necessarily separate them as different technologies, because they are not mutually exclusive, but really work better together. Users can write Spark code in the form of PySpark or Scala that can take advantage of rich libraries, packages, and functions that are available within the open source community. And Spark code can access all of the structured Hive datasets that are stored within the Amazon S3 buckets as it relates to that Hive architecture I went over earlier. And it can access those tables and databases by leveraging the same metadata information that's stored in the Metastore repository. So if there's one takeaway from the presentation around Hive and Spark, it is the fact that when you think of Hive, that technology and that framework contains structured Hive databases and tables that can be queried using HiveQL. And when you think of Spark, you can refer to that as the Python, R, and Scala programming languages that can access those Hive datasets. And in typical architectures, Hive and Spark are deployed across the same EC2 servers in a single cluster. And what you see here in this illustration are those sets of clusters that are typically available in a Spark and Hive cluster that allows for them to work in tandem with each other to be able to read data that's stored within S3 buckets. Moving on to the next subsystem is CAP. Within CAP, we have a primary application today called SAS Viya. And SAS Viya is a cloud-enabled in-memory analytics engine that provides quick, accurate, and reliable analytics insights. And it provides elastic, scalable, and fault-tolerant processing within a particular cluster to address all the complex analytical operations for your specific workloads. And very specific to SAS Viya is the support for Cloud Analytic Services, otherwise known as CAS. And this is the difference between SAS Viya as well, compared to older SAS processing models that are in the CAS 9 versions. And within CAS, Viya is able to leverage its in-memory engine as a fast, scalable, and resilient runtime environment for data management and analytics within the platform. And this provides access to that in-memory engine and allows also for in-memory datasets to be able to spill to disk as necessary. Specific components that are part of the SAS Viya applications today are individual services within SAS Viya that include SAS Studio, which is the main development tool in SAS Viya, in which one would log in to SAS Studio, create new programs to write their SAS code and to submit them from the web-based UI. It's also going to be within the SAS Studio that you can also access the workbenches where you can store all of your local files as well as any local data sets that are generated by your SAS programs. So recall, as I mentioned earlier, the introduction for some of the key services that we leverage today within AWS, one of which is the Lustre file system. The Lustre file system can be used to act as essentially a cache to be able to access data sets living in S3 buckets faster as part of your SAS programs. Moving on to another service that's important is the SAS Data Explorer, which will allow you to import data into SAS Viya, as well as see any existing cast-lib databases and tables that you have access to. There's also the SAS Visual Analytics, which is a tool for reporting, for data exploration analytics. However, its use today is quite limited, as we do recommend the use of AWS QuickSight, which is to be touched upon during the data camp sessions for all of your BI needs. SAS Viya also offers us access to an environment manager service that allows you to manage your scheduled jobs, getting insight into the systems, and perform other administrative tasks that might be more dedicated for the admin team. And then it also supports SAS accesses and connectors to other corresponding databases, including Hadoop, Redshift, Postgres, and SQL Server. The processing engine and the compute engines within SAS Viya can be broken up into two components. You can either run your SAS jobs leveraging the SAS programming runtime environment, otherwise known as sprees, which I've referenced in the past as spree machines to run these type of operations. And within these hosts, that engine is used by users to run operations that folks have historically written their SAS code in. And it's essentially that base SAS code that runs within this engine and run with it as a compute server session that's spun up within SAS Viya. CAS, on the other hand, processes and runs your jobs by spreading out the operations across all threads within the CAS worker nodes today, similar to the MapReduce paradigm. In the processing and the parallel processing of all of the data sets can happen also in memory and distributed within the workers, which can reduce the runtimes for your procedures and data steps. However, one thing to note is that not all procedures and data step statements are CAS enabled. We do recommend you limiting your use of CAS today, because unlike the Hadoop framework and leveraging MapReduce and Spark operations evenly across all of the machines, we have found that there are limitations using CAS because operations are not distributed equally, and you can find hotspots of your specific operations running on certain CAS workers, which can overtake the system and take over all of the resources on that machine. So the recommendation here is to limit your use of CAS as necessary, and instead take advantage of the fact that SAS Viya is able to connect to CDR, and within CDR we have the Hive engine to more evenly distribute all of your operations when it comes to aggregating and joining your specific data sets. This next slide covers the SAS Viya Architecture, in which it starts off with the SAS Studio V service, where you're doing our development, and in the left column you can see the workflow following operations that are run as part of the proc SQL statement, and on the right side are all the operations that are run when you're using the proc CAS util. On the left side, when the proc SQL statement is being executed, it gets sent to the compute service first, then that pushes it to the Spree machines to essentially be run, in which case oftentimes the jobs are accessing specific data sets within Hive, otherwise also CDR. And when it's connecting to Hive to submit the SQL statements, Hive is interpreting and analyzing the SQL statement, coming up with a query plan, coming up with the DAG, and distributing that operation across the Hive cluster. And within those Hive clusters, it's accessing data sets that are in Amazon S3 buckets, and then running all of the merge operations and aggregations to return back the results back to SAS Studio. If you're running proc CAS util statements, it gets submitted to the compute service, which sends that operation to the CAS cluster. And within the CAS cluster, it moves it first to the CAS controller, which almost acts similarly on the Spark and Hive side of things as sort of that driver, the master node, where sort of the driver program is running. Within the CAS controller, it is then from there distributing all of the operations to the CAS worker nodes. And this is where I mentioned earlier that we found limitations using CAS, that operations oftentimes are not being distributed properly, and there are hotspots within the cluster that can take up too much resources within the system. However, in those operations, in the worker nodes, it's pulling data from Hive in that particular case, and then holding them into in-memory data sets within CAS, and then running all the operations that are necessary according to your business logic within the code before returning back the results to SAS Studio V, or having those results saved as a SAS dataset that can be accessed downstream. Okay, now putting it all together to summarize what we've talked about. So again, CCSQ Environment includes two major subsystems: CAP, which stands for CCSQ Analytics Platform, and CDR, which stands for Centralized Data Repository. Both subsystems are deployed within the AWS cloud and work together to be able to support your analytics operations. CAP can be seen as a set of tools that users would log into, such as SAS Viya, is what I covered earlier, to be able to develop your code for your analytics workflows, where you can configure your business logic. And in that code, it can access the CDR, which is what's used for the data storage and for all of the data processing. And how it all fits together here, this next slide illustrates where on the right side, you have SAS Viya deployed across EC2 instances, and within the specific SAS Viya cluster, we have hosts and EC2 servers to support the Spree service, in which it runs the compute service processes within it. And then there are EC2 instances that are running CAS controllers and the CAS workers. And within the CAS workers, there are CAS services that are used to run your CAS util operations. In each of those two particular workflows, whether they are run on Spree or CAS workers, data sets are accessed by connecting to the CDR, which on the left side is being supported by the Hive service, in which we have EC2 instances that are configured to run Hadoop, where we have Hive services listening and ready to support the connections that you get from Spree and CAS workers. And then when those connections are made, when SQL queries are submitted, is looking into the Metastore to look at the project databases in order to pull the corresponding data files from the appropriate S3 buckets where those CDR datasets reside toward the bottom. And then when it's pulling it back to the Hive services, aggregations are happening depending on the SQL that was submitted, and pulling back the results back to the compute service within Stream Machines or within your CAS services and the CAS workers. SAS Viya also has access to Workbench files and file cloud files that are also hosted within AWS S3 buckets, taking advantage of the unlimited capacity that we have there. And it's going to be within these workbenches that would store your SAS programs, along with any files, local files that are generated by your SAS programs and saved to your workbenches. That those workbenches, even though they appear to be local to SAS Studio, are actually powered within S3, where we have access to all of the resilience and the backups. And when files are generated within Workbench files, within those workbenches, they can be also accessed by File Cloud in order for you to upload and download to your local computer. So to summarize, all of the technologies that are highlighted today can be found in this slide, including CAP, CDR, AWS, Hive, and SAS Viya. From the topics that are covered today, if you'd like to know more, there are plenty of resources available on the internet to get a better understanding of each of these services. However, there will be materials that are going to be shared from this data camp that you can also reference, including best practices as well as additional documentation that pertain to your specific workloads. Thank you for your time today. And please, at this point, you can submit your questions within the Zoom chat.
All right, and with that, that concludes our session. So we're going to go into the Q&A portion of the call. So far, we just received one question, but if you have more, feel free to put them in the chat. So Philip, question for you. From a high-level view, how will the new notebook alternative tool affect the architecture?
Great question. So the notebook tool would be the replacement for Zeppelin, which I referenced yesterday. And that would be the tool that folks can do their development in Python, R, Java, and Scala to run the Spark code. And then additionally, the decision on the new platform would essentially replace the current CDR Hive clusters that we have. And instead of operating on a single large cluster that all groups are connecting to, folks would have access to personal compute clusters in order to isolate their jobs from one another and be able to access resources that can auto-scale versus the static cluster that we have today.
Great. Thank you, Philip. And just to put a plug in there, yesterday's session was really informative for the notebook alternative tool. So for those who missed it, the recording of that presentation should be available on Monday out on our Confluence site. So that should be available for you guys to check out. And with that, I'm not seeing any other questions. So I think that concludes this session. Our next session will begin at 1 p.m. and it's on the Quick Site tool. So let's now go into a 15-minute break before our next session.